we're on to section 28, greatest common divisor, or we often shorten it to GCD. So here's the definition of that. We're going to let there be two integers, n and m. Both of them are not allowed to be 0. So two non-zero integers, n and m, then the greatest common divisor of m and n is written as all lowercase GCD, and then parenthesis m comma n and parenthesis. So that is the largest integer that divides both m and n. Okay, so that's why 0 is not allowed, because if you think about it, anything divides 0. So let's talk about an example. So maybe let's talk about what would GCD of 15 and negative 21 be. Okay. And you can try this on your own if you'd like. You just want to find the largest integer that divides both m and n. Okay. So let's think about, we can think about for 15 divisors. Those could be, well, let's only list the positive ones, because of course we have like plus or minus 1, but 1 already beats that, right? So if positive 1 divides both of them, and negative 1 divides both of them, well, 1's going to win, right? So let's just list the positive ones right now. So 1, 3, 5, and 15, okay? So 21 divisors, and you don't have to do this every time. We have 1. Okay, well we also have 3, right, because of 7. Okay, does anyone else? Okay, well 21. Okay, so sure, 15 is the biggest divisor of 15, but it doesn't have that in common with, oops, sorry, negative 21. But positive 21 also divides negative 21. Okay, so if the negative of something divides something, then the positive version of it divides it as well. So that one, that's okay, we don't care about that one. We don't care about that one because 5 doesn't divide negative 21. So that's the other way we could approach this. We could have just found these and then said which of these divides negative 21. Well, they do have that in common. They also have this in common, but 3 is bigger. So GCD of 15, negative 21 equals 3. Excellent. So maybe let's say that this is examples, and let's call this one number 1. Okay, so for number 2, what if we just pick like 2 integers, well, non-zero integers, m and n? Well, we talked about this a little bit, but then the GCD of m and n, whoops. Well, is it ever going to be less than 1? No, it's not. So it's always going to be bigger than or equal to 1. So it could be 1. Maybe that is the case, but it could also be bigger. Alright, so what if we did like m and p? So they're both integers, and p is prime. Okay, so let's think about p divisors. It's just going to be 1 in p. That's the definition of being prime. So, what do we end up getting? Well, now we GCD of m and p only have 2 options. So 1, if p does not divide m, and p if p does divide m. So yeah, up here we could have done something with 4 cases, right? But it's not that special. We could always do that, I guess. But with primes, this is very special. Okay, so for number 4, let's return back to just 2 generic integers, non-zero. Well, let's say that absolute value of n is less than or equal to absolute value of m. Okay? Because remember, they could be negative, and that doesn't really change anything. Well, something that we could say is that then m doesn't divide n unless m equals n. If if their absolute values equal each other, then of course they divide each other. So maybe how I should say this is, if absolute value of n is strictly less than absolute value of m, then m does not divide n. Right, because it's bigger, so how does that make any sense? Its absolute value is bigger. Okay, so something that we could think about with here is then the GCD of m and n has to be less than or equal to absolute value of n, because it's the smaller one, or maybe it is the same. So if m equals n, or if their absolute values equal each other, then it will just be absolute value of n. It'll be equal to that. So similarly to this, if n is some non-zero integer, then what's going to be the GCD of n comma n? What's going to be the absolute value of n? How cool is that? So also, if we think about, let's say n non-zero integers, then, such that q divides n and q divides m. So remember, for something to divide something else in this way that we're defining it, then it must be that q is an integer. Okay, a non-zero integer, because remember, we don't divide by 0. Okay, so then that gives us that actually the GCD of n and m has to at least be the absolute value of q. Okay, so this is very similar to our second example, where we always know that 1 divides any integer. So here, if we know that some integer q divides both n and m, then we know that the absolute value, our GCD has to at least be the absolute value of that. So it might be equal to absolute value q, or it might be bigger than it. We don't know, but it's at least that. Okay, it's not going to be something less than that, because that's already going to be bigger than whatever's less than it. Okay. So something else I just wanted to touch on as well is that these absolute values for the GCD, so if we have, let's again pick like 2 just generic integers, then any combination you think of, so GCD of m comma n is equal to GCD of the absolute value of both of them. It's equal to the absolute value of the first one, but not the second one. And it's also equal to the absolute value of the second one, not the first one. Because remember, absolute value is not really going to change whether or not something is a divisor of someone else. So like, for example, -2 divides 6. Sorry, let's just say 2. And 2 divides -6. Okay, so if p divides q, then p divides -q, whoever that may be. Okay. So it doesn't matter what absolute values, or maybe we for some reason we negate both of them, so we negate m, negate n, I don't know, it doesn't matter. Just as long as the absolute value of the integer stays the same. So what I do see sometimes is people use this because maybe it's easier for them to look at positive integers. So like if they're handed a question like, what's the GCD of -7 and 21 or something, they can rewrite it as GCD of 7, 21, and that's the same thing. And then we can work from there. Okay. All right. Oh, by the way, this is 7. Okay. All right. Awesome. I hope this was helpful. I'll end it here. Have a great rest of your day. Bye-bye.